Hello, dear students. Hope you are all doing well. This is Idris, the physics teacher at Paris Private School. After we finish with chapter 6, today we are going to talk about and explain chapter 7 about the interference and diffraction. In this chapter, as you know, we have three sections. Section 1 about the interference, Section 2 about the diffraction, and Section 3 about the lasers. In Section 1, we will focus on the combining light waves and demonstrating interference by using double slit interference. The interference of light wave, as you know, we studied the interference of the mechanical wave. The two mechanical wave can interference in order to produce constructive interference and destructive interference and weakening interference. We have the same thing, exactly the same thing in electromagnetic waves, such as a light wave, but the condition of interference of light wave is completely different with the condition of the interference of a mechanical wave, such as a water wave or the wave of the rope or sound wave. Guys, we start with the question, why the bands of color, the spectrum of the color, occurs on the surface of the soup bubble. During washing your hands, you observe that you will see the spectrum and the bands of the color when you are washing your hands by the soap, because the white light of the source contains several wavelengths, contains 7 different wavelengths, contains 7 colors. So each of the color, they interference at a specific interference. So they produce red light, orange, blue, green, indigo. Okay. So the answer of this question, because of the interference of light, the spectrum appears on the surface of the bubble of soup. These colors are results of what? Interference. Because of the interference, the colors occurs on the surface of the soup. And of the light wave is combining with each other. So what is the light or light wave? You know that the light is a part of the electromagnetic wave, which is oscillating the electric field and magnetic field. Is an electromagnetic wave. Its speed is constant in vacuum, 3 times 10 to the power 8 meter per second. This is the speed of light. And those wavelengths of the light that the human eye can see between. So the light is the visible wave of the electromagnetic wave of the electromagnetic radiation. And the human eye can detect the colors and the light wave from 700 nanometer to 400 nanometer violet. From red, between 700 nanometer red and 400 nanometer violet. So we have 2 different types of the source, monochromatic source and polychromatic source. Source of light. We have 2 different types of the source of light. Monochromatic and polychromatic light. So what is the difference between monochromatic light and polychromatic light? A monochromatic light, a source that consists only one wavelength or a single color. Monochromatic source is a source that contains only one wavelength or one color, such as the laser, like for example the red laser, green laser, yellow laser, or any other sources that has like red brightness and yellow, green, blue color. Okay. So the monochromatic light is a light that has only one color, that has only one wavelength, such as red, green, yellow, something like this. Okay. But a polychromatic source is completely different with the monochromatic. Another source of polychromatic light consists of several colors, or consists of multiple colors or multiple wavelengths, such as white light. The white light that you can see at home, this is a polychromatic light. Okay? The white light is a polychromatic light. Why? Because this white light contains several wavelengths, contains many different colors like red, orange, yellow, green, blue, indigo, violet. Okay? So this is basically the difference between polychromatic and monochromatic light. Okay. So the visible light range starts from red 700 nanometer until violet 400 nanometer. Monochromatic, a light source that has single wavelength, which means single color. Monochromatic light such as red, yellow, green, blue, and violet. White light is considered to be a polychromatic in nature because it consists of light having several different wavelengths. Interference takes place only between waves with the same wavelength. So this is very important. Be careful, guys. One of the conditions of the interference in order to occur in a light wave, the two waves must have same wavelength. When does the two light wave interfere to each other? If the two light waves, they have the same wavelength. Like for example, two sources, red and red, can they interfere with each other if they passes through the same position and through the same slits? Yes, of course. Why? Because the two red light, they have the same wavelength. Okay, if they are in phase or if they are coherent. How about if the two light comes out from the double slit interference with different color, green and blue? Can they interfere each other? Does the interference occur between green and blue if they emit from the double slit interference? Absolutely no. Why? Because the two different colors, they don't have same wavelength. Each color has its own wavelength. So the wavelength of the red has the largest wavelength from crease to crease. But orange is smaller than red. Yellow smaller than blue. Green smaller than yellow. Blue smaller than green, and the shortest one is wavelength. As we are moving down, what happened to the wavelength? The wavelength decreases. Each color has its own wavelength. No two colors have the same wavelength. Okay? And the two colors have two different colors have different wavelength. For example, the wavelength of the red light assume that this is red light, largest wavelength. But violet has more frequency, but less wavelength. This is longest wavelength, this is shortest wavelength. Okay, so this is the difference between the wavelength between these two colors. If two waves with the same wavelength interact, they combine to form a resultant wave. This resultant wave has the same wavelength. The resultant wave also has the same wavelength. For example, if we have two yellow source, this is source number 1, this is number 1, and this is source. No, it must have the same wavelength. Look, this is source number 2 and this is 1. Which one has more wavelength, number 1 or number 2? Both, they have the same wavelength. If two light waves, they have the same wavelength, can they interfere with each other? Yes, absolutely. Okay, because one of the conditions of the interference of the two light waves must have same wavelength. So what will be the resultant wave here in this case, guys? Lambda of resultant wavelength is equal to what? Is equal to lambda 1 is equal to lambda 2, because the resultant wavelength, assume that the green one is the resultant wave, and the resultant wave we have to add them together. So the resultant wavelength, still they have the same wavelength. Yes, the resultant wavelength, the result of the interference of the two individual waves, they have the same wavelength. Okay, if they bring in the Wizari exam, for example, and also it has been brought in the Wizari exam, the two wavelength interference with the same wavelength. Which of the following is corrected for the resultant wavelength? The resultant wavelength exactly is the same of the two individual wavelengths? Yes. Is it possible to say the resultant wavelength bigger than the individual? No. The resultant wavelength still the same. But amplitude, the amplitude, so we have to add up the two individual amplitudes. So the brightness increases here. According to the superposition principle, it is displacement at any distance equal to sum of the two displacements and the component waves. The resultant wave is the consequence of the interference between the two waves. What are the conditions of interference of two waves? What are the conditions of interference of two waves? The source of the light should be monochromatic, single color, okay? And the two waves have the same wavelength. The two waves must have the same wavelength. And the two waves should be constant phase difference or coherent. Okay? What is the coherent? We have two different types of coherent. Guys. Or coherency. Coherence by zero and coherence by 180. Coherence by 0 or 2 pi is like this. For example, if we have two waves, both start with the same, at the same point. So what is the phase difference between these two waves? 0. Why? Because what we have here is 0, here 90, here 180. 270, one complete cycle 360 plus 90, it's gonna be 450 and go on, okay? So the below wave, this wave also starts with 0, 90, 180, 270, 360. Guys, look, 0 minus 0, 0. 90 minus 90, 0. 180 minus 180, 0. 270 minus 0. So, can we say these two waves are coherent? Yes, of course. Why? Because the two waves do not shift each other, and the crease overlap with the crease all the time, trap overlap with the trap all the time. So, when crease adjacent with the crease, trap with trap, can we say these two waves are coherent if they have the same wavelength? Yes. So, if crease overlap with crease, trap with trap, can we say this is coherence by 0 degree? Yes. So, this is constructive or destructive? This is constructive. Coherency by 0, always constructive. Okay? Another type of coherence by 180. When does this coherence occurs in between the two waves with the same color? In this case, assume that the source is blue. It doesn't matter, okay? Guys, look. The first wave start here, 0, again 90, 180, 270, 360. The second wave does not start at this point, okay? The second wave start here. Okay, sorry. Look. When the wave start here, 0, do we have wave here? No. 90, do we have? No. This is 180. Angle is equal to what here? 0. 180 minus 0, 180. Here 270, but here we have 90. 270 minus 90, still 180? Yes. The angle for the second wave here is equal to 180, but here is equal to what? 360. 360 minus 180, it's still 180? Yes. So the wave, can we say the wave is coherent? Yes. Why? Because the phase difference is 180. Okay? When does the phase difference has 180 degree or coherent by 180 degree when trough of one wave, the trough of one wave overlap with the crease of the second wave or another wave. Okay, so can we say the interference takes place between these two waves? Absolutely yes. Why? Because the two waves have the same wavelength, single color, and they are coherent by 180 degree. But this type of coherent is a destructive interference. Crease with trough, trough with crease, it becomes what? Destructive interference. Destructive interference. Okay? So this is very important for the student to keep in mind that we have two types of coherence, by 0 or by 180. 0, phase difference between two waves must have 0, which means crease of one wavelength overlaps the crease or another wave. And the type of the interference is constructive, such as in this figure. Trough, trough, crease, crease, trough, trough. Phase difference 0 all the time, coherent by 0. But 180, crease with trough, trough with crease, coherent by 180. The type of the interference is destructive, and the dimmer region appears, or the dark fringe appears. Interference in sound recognized by difference in volume. Interference of sound recognized by the volume. When the volume increases, it means that the interference is constructive. So how is the interference in light recognized? By brightness or by intensity of the brightness. Okay, by difference in brightness. The types of interference, guys, it's very easy. We have three different types of interference. Constructive interference, and weakening interference, and destructive interference. In constructive interference, when does the constructive interference occurs? If the two waves interference with the same wavelength and the phase difference between them must be 0. The phase difference must be what? 0. The two waves should be coherent, but coherent by what? By 0 or by 180? By 0. Okay? When does the two waves considered to be a coherent by 0 degree? If the crease of one wave overlaps with the crease of another. Trough with trough, crease with crease. As you can see in this figure, this is first wave, this is first wave, and this is second wave. How many waves do we have? 2. Is 2 waves, they have the same color? Yeah. Same wavelength? Yes. Which one is bigger? Lambda 1 or lambda 2? This is lambda 1. This is lambda 2. And this is resultant. The lambda of resultant. All they have the same. In interference of light, the wavelength does not change. Resultant wavelength is equal to the individual wave. So can we say these two waves are coherent? Yes, this is coherent, but coherent by 0 or 180. So you have to take a look. Crease with crease, phase difference 0. Trough with trough, phase difference 0. This interference constructive or destructive? This is constructive. Why? Because crease overlap with crease, trough with trough. Okay? What are the conditions of constructive interference to be occurred? The two waves must be in phase, 0 phase difference. The phase difference between them must be what? 0. Coherent by what? By 0. They have the same or different amplitude. It doesn't matter. Okay? It doesn't matter which one. Like the two waves, they have the same amplitude or they have equal amplitude. Okay? It doesn't matter. They have the same wavelength. So these are the conditions. The resultant wave will be what? This is the resultant. The amplitude of the resultant wave is greater than the amplitude of either of the individual component wave. This is amplitude of the first wave, and this is amplitude of the second wave, and this is the amplitude which is largest of the resultant wave. It is light is brightest than the light from the contributing waves, and the bright fringes forms. The bright fringe forms in constructive. Which type of fringe produced in constructive interference? The bright fringe. The resultant wavelength or wave has the same wavelength of individual wavelength. Lambda result total is equal to lambda 1 equal to lambda 2. But A, you have to add up the individual components. Weakening interference. In weakening interference is completely different with the constructive interference. In weakening interference, the two waves still must have the same wavelength, and still they should be coherent, but the coherent in weakening and destructive is completely different with the coherent of constructive. The coherent in destructive and weakening interference, it should be coherent by 180. When does the two waves has coherent by 180 degree? If the crease of one wave overlap the trough of another wave. Okay? As you can see in this figure, this is first wave and this is second wave. How many waves do we have? Two. One, two. One, two. This wave is creased, but this one is what? Trough. If you see two waves, one of them creased and the other is trough at the same line, the coherence between these two waves is 180. When the two waves has coherent 180, the type of the interference is weakening or destructive interference. Why we cannot say this is destructive interference? Because the two amplitude, the two amplitude of the individual wave, different amplitude. What is the condition of the weakening interference? The two light must have the same wavelength, and the two light wave must have a coherent in 100 by 180, and the amplitude of the individual waves should be different. Guys, be careful. This point is very important. What is the difference between weakening interference and destructive interference? In destructive interference, the two amplitude must be the same. Crease with the trough, the amplitude of crease and the amplitude of the trough must have the same value. But in weakening interference, the two amplitude must be different. What are the conditions? The two waves have phase difference 180, out of phase, different in amplitude. One of the amplitude is bigger than the other one. They have the same wavelength. The resultant amplitude is less than the amplitude of the larger component, as we studied in mechanical interference, chapter 3, section, I think section 3, yeah? The intensity of the result light is weak or low intensity dimmer fringe appears. The resultant wave has the same wavelength of individual wave. Destructive wavelength, so you have to subtract them. In destructive, the two waves still must be out of phase, like in weakening, phase difference 180, but its amplitude has the same magnitude, but in opposite direction. In destructive interference, the amplitude of the individual waves must have the same amplitude. Okay? Like in this two wave. Same amplitude. Okay? The resultant will be straight line. The amplitude of the resultant wave is 0. Resultant amplitude is equal to what? 0. The result of destructive interference is dimmer light or dark spot or dark fringe forms. What happens if two light waves with the same amplitude? With what? Same amplitude. A1 is equal to A2. Okay? Interfere constructively. The resultant amplitude becomes twice. If the two waves with the same amplitude interferes constructively, what will be the resultant amplitude? Twice. How about, and what happens if they interfere destructively? It's gonna be 0 because they have the same amplitude. The first part, the amplitude of the resultant wave is twice the amplitude of the either interference wave, so the bright fringe forms. But for the second case, destructive, the amplitude of the resultant wave is 0. Okay, and the dark fringe forms. Wave must have constant phase difference. We studied. When is the difference between the two waves steady or continuously? When the waves have constant phase difference. Coherence by 0 or 180. This is coherence crease with crease, coherence by 0, but this is coherence by 180. This is constructive, crease with crease. This is destructive. Okay? When does the two waves are said to be in phase? If crease with crease overlap with crease, trough overlap with trough. And when does it consider to be out of phase or 180? If crease overlap with trough. If the phase difference between the wave change, the waves cannot be coherent. it becomes incoherent, such as these examples of incoherent wavelength. Can we say these 5 colors are coherent? No, because they don't have same wavelength. What is the conditions of the coherency of the two waves? The two waves must have the same wavelength. Okay? Like a light bulb, the light from the light bulb considered to be incoherent. Why? Because the light bulb contains several colors, contains multi-colors or many colors, such as red, green, yellow, okay? But it appears to be white, but actually it is not white, okay? So they are not coherent. When the light bulbs are placed side by side, when two light bulbs are placed side by side, no interference is observed, even if the light are from the same color, because the two waves, maybe they are not coherent, okay? Like for example, if you have two yellow light, okay, this is the wavelength. It doesn't necessarily every two colors interference each other. No. In this case, we have two colors, we have two sources with the same color, same wavelength. But we don't have interference of these two light. Why? Because they are not coherent. They are not coherent. When does the two light with the same color, with the same source, they interference each other? If they pass through the double slit barrier. Okay, we will study the double slit interference here and demonstrating the interference. Because the phase difference between the light waves from the two bulbs are not constant and or incoherent. Because of their great distance from us, stars are essentially point source of light. If two stars were near each other in the sky, would the light from them produce an interference pattern? No. Why? Because they are not coherent. The two stars side by side, two light waves, two white light, they do not interference because they are not coherent. No, because light from the stars are not coherent. Demonstrating interference. This is very important, guys. Be careful. In this demonstrating, we can find the dark fringe and the bright fringe that appeared on the screen as a result of the interference of the two waves, maybe constructive interference and destructive interference. Now I'm going to show you this simulation about the double slit interference. I'm sure that will be very helpful for the students. Guys, look. We have a source of light, okay? A light generator. We have a source of light. And the type of the source of the light is monochromatic. Why? Because it is a single color, okay? Monochromatic light is a light that has only one color. And we have this barrier. So what is this? This is barrier, okay? If the barrier is placed in the front of the source, okay, and we have two slits, so we can make one slit. Now we have one slit, but now we have, look, we have two slits, okay. Guys, now we have a source of light and a barrier that contains two slits, okay. So this is screen, okay. This is screen, and when the light passes through the two slits, when the single color, the monochromatic source, passes through the two slits, the dark fringe and bright fringe appears on the screen. Why? What is the meaning of dark fringe and bright fringe on the screen? In a region when the dark fringe, or in the region when the bright fringe occurs, it means that the type of it means that these two waves interfere each other. So the interference takes place between these two waves, and the type of the interference is constructive. When the bright fringe. When you see the bright fringe indicates that the two waves are in phase and the type of the interference is constructive. But for the dark fringe, be careful, the dark fringe indicates that the two waves are out of phase and the phase difference between them is 180, but they are still coherent. Coherent by what? By 180. Okay, but these two waves, they cancel each other and the resultant amplitude becomes zero. So that is why the region becomes dimmer and the dark fringe produced. Let's get started. Guys, look. The source is red light, okay? When they pass through these two slits, guys, look. What is the advantage of the double slit interference? Guys, when the light of the portion of the wavefront passes through the slit, and also when one of the portion of the light passes from this slit, these two slits act as a source. Now, before enter the barrier, the double slit interference, we have one source, okay? But when the light passes from these two sources, because the light behaves as a wave, so they can diffract, okay? As a result of this diffraction, each portion acts as a source. Now, assume that it appears, not really, it appears we have two sources with the same color, and they can interference to each other, okay? Look. Sorry. Each slit acts as a source according to Higgins principle. The Higgins was the first scientist discovered with this phenomenon. Look, now you can see bright fringe and dark fringe. Okay, I hope you see this. Look, I see the bright fringe here and dark here. Bright, dark, bright, dark. A series of bright fringes and dark fringes appeared on the screen. Bright fringe indicates the constructive interference, and the dark, it means that the type of the interference is destructive interference. Okay, so you can do with the different colors. Now let's do it with the green. Look, they interfere here, and look, you can see the dark portion here. Look, bright, dark, bright, dark, bright, dark. This one is more clear than the red. Okay. Okay, guys, hope you get benefited from this simulation, and I'm sure that this is very helpful for the student to make it easy, because sometimes the students are struggling with the interference of the two light waves. Okay, let's go back to our pamphlet. Okay, guys. This is the demonstration of the double slit interference. What are the benefits or advantage of the double slit interference experiment? Demonstrating the sample of interference. By using the double slit interference, we can demonstrate the sample of the interference, which is bright or dark, and wavelength measurement of monochromatic light and dispersion of the polychromatic light into a multicolors. How dark and bright fringe formed in an interference. This is interference, not diffraction. Okay, because the slits act as a pair of coherent light source according to Huygens principle, and the emitted light from the slits interference, therefore the bright fringe produces as a result of constructive interference, and dark fringe produces as a result of destructive interference. Why the central fringe is always bright? Guys, look. Now I'm gonna do the same thing. I'm drawing how the dark and bright fringe produced. Assume that this is source, okay, and this is a barrier located in the front of the source, okay, and we have two small slits here and here, okay? Guys, this distance is called the slit separation. The slit separation from this slit to this slit, okay? And this is the wavefront that comes out from the source, okay? And assume that there is a screen here. But let's make the background white. Sorry. Okay, this one is better. Okay, we have a yellow light, so let's change the color. I think the red is better. It's more clear than the yellow. It has more wavelength, so that's why it's more clear. Now I'm going to change the color. Okay, assume that the source is red. Okay, this is the wavefront. Each portion of the wavefront when passed through the two slits acts as a source. And assume that we have a screen here. Okay. Assume that this is screen. When the light passes through the two slits, the light diffracted when they passes through the slits, okay? But for the first one, guys, in double slit interference, when the light passes through the two slits, the central of the screen always becomes bright fringe, okay? The central fringe, which is called the central maximum, always becomes what? Becomes the same color of the source. What is the color of the source? Bright. The center of the screen has bright or dark? Bright. Always? Yes, always. The central fringe always becomes bright and it has the same color of the source. Why the central fringe is always bright? Because the type of the constructive there is constructive and the path difference between them is 0. Guys, look. This is wave. How many wavelengths do we have? Vibration. 1, 2, 3. Okay. Look. Because at the center of the screen, what is the type of the interference? Constructive. Crease with crease. Look. Crease with what? With crease. Look. Crease with crease, trough with trough. And the type of the interference becomes what? Constructive interference. In constructive interference, bright fringe or dark fringe appears the bright fringe. Okay? But above the bright fringe, the dark fringe will occur here. Why? Now I'm going to explain. This one is called M is 0. M is equal to what? 0. Why? Because located exactly at the center of the screen. M is equal to what? 0. This is central maximum, or this is the central bright fringe. We cannot say first bright. This is not first. This is central bright fringe. Okay? But this one, when M is equal to 0 for the dark, for this dark, M is equal to what? M is 0. Does the dark fringe located at the center of the screen? No. The dark fringe does not locate at the center of the screen. Locate above the central maximum, which is bright. So that is why we cannot say this dark is central dark fringe. We don't have central dark fringe. Only we have central bright maximum. Okay. So this dark fringe is called what? First dark fringe. What is this? First dark fringe. Dark fringe. This one is first dark fringe. How this first dark fringe occurs? Let's delete this one. What is the conditions of destructive or complete destructive interference of the two waves? The two waves must have 180 coherency, or coherent by 180. Okay. In this case, look, guys, this is trough, but this is creased. Okay. Phase difference between them is what? Is 180. When trough overlap with creased, creased overlap with trough, the type of the interference is what? Destructive interference. In destructive interference, dark fringe or bright fringe appears dark fringe. Okay? So that's why it's gonna be what? Ferrous dark fringe. After that, this one becomes what? Becomes M is equal to 1. This is ferrous bright. What is this? This is ferrous bright. In ferrous bright, guys, look. In ferrous bright fringe, now I'm going to do it one by one. In ferrous bright fringe, they are still constructive, yes. But which one, which light is near from this bright, which slit is near than near from this bright fringe? Absolutely the slit number 1. This is slit number 2. So which slit is near from the ferrous bright, from M1? Slit number 1 or slit number 2? Absolutely slit number 1. Slit number 2, it takes more distance to reach on the screen. So the difference between them is equal to what? Look. But they are still constructive, yes. But phase difference here is equal to what? Phase difference is equal to 2 pi. Sorry. Phase difference is equal to what? 2 pi. But phase difference here is equal to what? 0. Okay? Another bright appears well here. On here, sorry. But here phase difference is equal to what? 6 pi. Here it's gonna be 8 pi. Okay? But for the dark fringe, first dark fringe, which M is equal to 0, phase difference is equal to what? Pi. For this one, phase difference is equal to what? 3 pi. This one, 5 pi. The odd number multiplied by pi? Yes. Okay? So this is the phase difference that occurs the dark fringe in the double slit interference. For M1, this is M1 and this is M2. This is M2, second bright. M3, third bright. What is the difference between path difference between M0 with M1? Path difference is equal to 1 lambda. 0 with M2, path difference 2 lambda. 0 with M3, path difference 3 lambda. What do you mean by this? It means that the second slit is furthest from the bright fringe according with the first slit by 3 wavelength. Okay? By what? By 3 wavelength. Now look, guys, look for the for M3, third bright, for the third bright, distance from slit number 1, slit number 2, here. So the path difference is equal to what? Is equal to 3 lambda. So what do you mean by this 3 lambda? It means that this wave that emits from source number 2 is furthest or largest than wave that the first wave that emits by slit number 1 by 3 lambda. For second order bright fringe, for the second order, second bright fringe, look, what will be the path difference? The path difference for the second one, path difference is equal to what? 2 lambda. It means that the wave that emits from slit number 2 is furthest from the wave emitted by first slit by 2 wavelength. Okay, so in this way, the dark fringe and the bright fringe occurs, and I wrote all situations for the dark fringe and the bright fringe on the Malzana. Why the central bright fringe forms at the location, the center of the screen? Why the central fringe always bright? Because the central bright fringe is a result of constructive interference, and the path difference is 0. Why located at the center of the screen? Because the two coherent waves have traveled equal distance. Path difference, guys, look. For the first bright fringe, for the central maximum, for the central bright fringe, the path difference and the distance of the waves that comes from the slits traveling with the same distance. Look, the central maximum. This is wave number 1. This is wave number 2. Which one has more distance from the slit? Same. If they are the same, path difference is equal to what here? Do we have path difference? No. Path difference is equal to 0. The two waves traveled with the same distance. Okay? Okay, because the two coherent waves have traveled equal distance, thus they arrive in a phase, so the constant interference occurs and bright fringe forms. What happens if the source of monochromatic light is used to demonstrate the interference pattern? The central bright fringe will produce as the same color always, and the series of bright and dark fringe occurs. What happens if the white light used? Guys, if the white light is used to demonstrate the interference of the light in double slit interference, we don't have dark fringe and bright fringe. Instead, the multicolors and the bands and the spectrum of the colors occurs or forms on the screen. Okay, so the bright fringe will be blurred. Okay, the multicolors, the rainbow forms, as you can see in this figure. But the center, it's still white. Yes, guys. In this case, we have white light. If we use white light in double slit interference, the central maximum also is white. Yes. Okay, but the other, the spectrum occurs. This is exactly what I studied here. Describe it. For the central maximum, the type of the interference is constructive. Here, the distance is one wavelength further from the other, and here the destructive interference occurs. Okay. Question number 7. Assume that white light is provided by a single source. Look at this question. White light is provided by a single source in double slit experiment. Describe the interference pattern if one slit is covered with red. Look, assume that we have a white light. Let's check. Let's change the background of the whiteboard. Okay. If we use a white light, this is white light. Okay. And this is the barrier. So if we have two single slits, but one of them covered with the red, one of them covered with the red filter, we have a red filter, and the other with the blue filter. With what? With blue filter. As you know, when the white light passes through the red filter, because this light contains seven colors, only the red light emits from this slit. Only the red light emits from this source. Okay? And for the other slit that covered by a blue filter, only the blue light emits. So these two colors can interfere each other? Absolutely no. Why? Because they have different wavelength. two different wavelengths can never interfere each other, The conditions of the interference to be occur between two waves, the two waves must have the same wavelength, which is same color. We don't have interference here. No interference observed. No interference observed because the two waves have different wavelengths. Predicting the location of the interference fringes. As you know, we have path difference, d sine theta. This is the two slits. Okay. And assume that this is green and the source is yellow, for example. The central becomes yellow, but here it becomes dark. Okay, and also yellow, bright fringe, dark, bright fringe, dark, and so on. Okay. For the first central bright fringe, path difference is 0, but for this one, for the first bright fringe, we have path difference. Guys, be careful. What is this? This is distance. Distance between what? The two slits. The slit separation. Distance between the two slits is called the slit separation distance, or D. Okay. For the first bright, this is M0, but this one M1, M2, M3. The first order, which is central maximum, always M is equal to 0 here. This is not first order because located exactly at the middle of the screen. Okay, but this one is M1, M2, M3. M1 with M2 path difference 1 wavelength, but M2 with M0 path difference 2 wavelength. M3 3 wavelength. Like with M2, do we have path difference? Yes. Okay, this is called path difference. What is this? Path difference. Okay, this one is hypotenuse, and this is the angle, opposite of the angle. Okay, sine theta is equal to what? Path difference divided by what? By d. Path difference is equal to what? If you rearrange, path difference is equal to d sine theta. Path difference is equal to what? D sine theta, according Pythagorean theorem. Opposite over adjacent. Sorry, over hypotenuse. Hypotenuse d, and opposite is path difference. Sine theta, opposite over hypotenuse, opposite path difference. Hypotenuse distance, the separation. Path difference is equal to what? D times sine theta. Okay, which is equal to d sine theta. The difference in the distance traveled by the two beams when they are scattered or emitted in the same direction from the different points. Or the number of the bright fringe and the dark fringe. What does the path difference depend on? It depends on the theta and the slit separation of the two slits. If the distance from the slits, the circle is very large compared with the distance between the slits, L1 and L2 are nearly parallel for a large distance. The angle also indicates the position which waves combine with respect to the central point of the viewing screen. The value of path difference, which is d sine theta, determines what? Whether the two waves in phase or out phase. Okay? When they arrive at the viewing screen. So this leads us to know the type of the interference. Under which condition bright fringe produce constructive interference. What do I mean by bright fringe? Constructive interference of light. Okay? Okay. Under which condition the bright fringe produce? When we say bright fringe, it means that the constructive interference between the two lights. When does the constructive interference occurs between two different waves and the bright fringe appears on the screen? If the path difference is either 0 or some whole number multiple of wavelength. Okay? When the path difference is equal to what? 0 wavelength or 1 wavelength, 2 wavelength, 3 wavelength, okay? Whole number multiplied by wavelength, okay? When does the interference between the two waves becomes constructive and the bright fringe occurs? If the path difference is equal to what? Whole number multiplied by wavelength. Whole number, according math basic, including 0, 0, 1, 2, 3, and infinity. Okay? Multiplied by what? By wavelength. This is the conditions of the constructive interference between the two waves. Guys, if you remember, we studied that on the screen, at the middle of the screen, the bright fringe appears, which is m is equal to 0. When the path difference is equal to 0, the two beams emitted from the two slits exactly with the same distance, m is equal to what? m0. We cannot say this is m1. This is 0 order maximum. But when the path difference is equal to 1 wavelength, order number is equal to what? m1. Here, m2. Here, m3. Okay? So when path difference is 0, phase difference 0 degree. But for one wavelength, one complete cycle, how many degrees do we have? 360 degree or 2 pi? This is 2 pi and 4 pi, 6 pi, 8 pi, and go on, okay? So when does the bright fringe produce or constructive interference occurs? If the path difference is either 0 or what? Some whole number multiplied by wavelength. The two waves are in phase, so the bright fringe forms. This is the equation of bright fringe. Okay, this equation is very important. D sine theta is equal to what? M lambda. D sine theta is equal to what? M lambda. What is this? This equation is very important to find and to solve the question that to determine the distance between the two slits and the angle of diffraction or the angle of the pattern of the bright fringe and the order number or wavelength. Okay, this is the equation of what? Bright fringe. Okay, so this is very important. Be careful. What is the slit separation angle? The pattern, the angle of the bright fringes compared with the central. M order number and lambda is wavelength. So this positive and negative is not important. Indicators that above the central we have to count for the positive, and below the central we have to put the negative sign. Okay, not important. Always for all questions you assume that it's positive above the central. And M is the order number, whole number. Okay, cannot be decimal number like 1.2, 1.3. It's always should be a whole number. Guys, I made a table here in order to understand easily. Constructive interference, the bright fringe, for bright fringe, constructive interference, M is equal to what? 0, 1, 2, 3. What do you mean by M0? The central bright fringe. When M is equal to 0, path difference is equal to what? 0. When path difference is equal to 0, phase difference is equal to what? 0. When phase difference is 0, which type of fringe appears? The central bright fringe. Central bright fringe. Okay, for M1, what do you mean by M1? M1, first order maximum, first order fringe, first bright fringe. It has several names. What do you mean by M1? First order maximum, first order fringe, or first bright fringe. When M is equal to 1, path difference is equal to what? 1 wavelength. Phase difference, 2 pi. It is named first bright fringe. For M2, path difference, 2 wavelength. Phase difference, 4 pi. Second bright fringe, and so on for others. Okay? The central bright fringe, theta 0, M0 is called 0 order maximum or central maximum. So this is the conditions of the constructive interference of the two waves. Another question, under which condition the dark fringe? So this time we have what? Dark fringe produced and destructive interference. When the path difference is an odd number. Odd number, what do you mean path difference? Guys, be careful. Path difference. If you remember in constructive, we said if path difference is equal to whole number multiplied by wavelength, the constructive and bright fringe occurs. But if the path difference is equal to odd number, what do you mean by odd number? 1, 3, 5, 7, 9, and go on, okay? Odd number multiplied by what? Multiplied by half wavelength. Multiplied by what? Half wavelength. Under what condition the dark fringe appears on the screen? When the path difference, listen carefully guys, when path difference is equal to an odd number multiplied by what? Half wavelength. Look, 1 times half wavelength, half wavelength. 3 times half wavelength, 3 over 2 wavelength. 5 times 1 over 2 wavelength, 5 over 2 wavelength. For 7, the same thing. Okay? So in this path difference, the direct fringe appears. When does this direct M is equal to what for this one? M is equal to 1. Because for direct fringe, we don't have M0. Because direct fringe does not locate at the center of the screen. This is called the first direct. First direct, sorry, M0, not 1. First direct. This is what? First direct. M0. This one. Second direct. M1. This one. Third dark, but M2, the number of M is always less than by factor 1 of its name. Like when we say first dark, less than first, 0. Second dark, 1. For second dark, you have to say M1. For third dark, M2. For seventh dark, M6. Okay? This is the conditions of the direct fringe occurs on the screen. And when M is equal to 0, phase difference is equal to what? Pi. What we have here? 1 pi. Here, 3 pi. 5 pi. 7 pi. So you can take advantage from the path difference to determine the phase difference. Phase difference for 1 over 2 wavelength, M is equal to 0, first direct is equal to what? In numerator, what we have? 1 pi. Phase difference for this one, 3 pi. For this one, 9 pi. For this one, 7 pi. Okay? When the path difference and odd multiple half wavelength, the two waves arriving at the screen out of the phase and the direct fringe appears. So the equation of the direct fringe is equal to d sine theta is equal to what? M plus 1 over 2 wavelength. What is this? This is the equation of direct fringe. So it is very important to recognize the equations. The equation described is the direct fringe or bright fringe. It should be indicated in the question, okay? Look, when M0, its name is equal to what? First direct fringe. M1, second direct fringe. M2, third, okay?